So let's calculate the pH of a solution that contains 0.2 molar nitrous acid and 0.1 molar potassium nitrite. And we have the Ka for nitrous acid is 4.5 times 10 to the minus 4. So the first thing we're going to do is set up an ice table. So we need to write out the equilibrium for nitrous acid. It's HNO2 aqueous plus water in equilibrium with NO2 minus aqueous plus H3O plus. Then we can set up our initial concentrations. And from the problem, we know that we have 0.2 molar HNO2 and we have 0.1 molar KNO2. And for every one KNO2, we're going to get one NO2 minus. So that's 1 to 1. So for the change, we do have one reactant present. Water we're not going to worry about. And we do have some product present. But we don't have any H3O plus, no hydronium ion present. And so with that, we know that some products must be formed to reach equilibrium. So we're going to have minus X for HNO2, plus X for NO2 minus, and plus X for H3O plus. So at equilibrium, we're going to have 0.2 minus X for HNO2, 0.1 plus X for NO2 minus, and X moles per liter of H3O plus. So then we can set up our acid equilibrium constant, Ka, is equal to 4.5 times 10 to the minus 4, and that's equal to the concentration of products. So for NO2 minus, it's 0.1 plus X times X divided by 0.2 minus X. So now at this point, we can make the assumption that X is small compared to 0.1. And small compared to 0.2. We can divide the concentration by the Ka, so the initial concentration divided by the Ka, and we'll get, for this, we'll get about 200. And for 0.2 divided by the Ka, we'll get about 400. So my previous rule was that if you divide out the initial concentration divided by the Ka and get a value around 1,000, your assumption is good. For this, I'm going to say that we're going to assume that this is okay, and we're going to check our answer at the end. It's much easier than doing all of the algebra that would be required for this problem. So with that, we're going to cancel out the X values that are inside the parentheses and either added or subtracted from a value. And so we'll end up with 4.5 times 10 to the minus 4 equals 0.1 X divided by 0.2. And we can solve for X. And we'll find that X is equal to 9 times 10 to the minus 4. And that's equal to, if we can write it out in decimal form, this value. And then by comparison, we only have two significant figures in our smallest, in both of these values for concentration. So if we were to have added X to 0.1, we would still end up with 0.1, because it would be 0.100 1009, which is 0.1. So our assumption is valid, is basically what I'm trying to say. This amount here is negligible. Okay, so x from, if we go back to our ice table, x is equal to the hydronium ion concentration which is 9 times 10 to the minus 4, and we were asked to find the pH. So the pH is equal to minus the log of 9 times 10 to the minus 4, which is 3.05. So you can compare this calculation. So this is when we have both HNO2 and NO2 minus in solution. But you can compare this to a solution that only has HNO2. And this would be a 0.2 solution, 0.2 molar solution. And that has a pH of 2.02. So you can see that the pH has gone up when we add in the nitrite ion. And what that's suggesting is that there's less H3O plus formed. And that's what we expect because our equilibrium shifts more towards the reactant side compared to when there isn't any nitrite present.